Okay, let's start it. Actually, if what I'm going to do is, let me write a model here. Okay, I wanted to put my y and x here. Okay, then you can run the data and also can see the model which we're working with. So this one is CO. Okay, and this is YD. Okay, so if I have t minus 1 here, so this is CO t minus 1, and this is t, and this is t. Okay, so if I express this as a distributed lag model, then again, this is COT, and all this is YD. This is t and YD, t minus 1, etc. Okay, understand? Understand what we're working with? So I'm going to use the OLS model to run this one as well as this one. Okay? Before we run, according to what we have learned, we're expecting what? This variables, this coefficient. We estimate the coefficient, which is from, this is lambda, and beta 0. So this coefficient do have relationship with this dynamic model's coefficients. Okay? All right? Then let's see whether we have this result. Understand what I'm saying here? Okay, so I'm going to use the eViews. Then you're going to use the Python, then you can use it, okay? And I'll show how to use using the eViews. All right? So this is the eViews. And I'm going to run using CO as a Y and YD as an X, okay? So first of all, I'm running 12.3. Then I run 12.9, okay? All right? So open as an equation. Okay, so since I need to have one more x variables, which is the lag of y. Okay, so what I do here is using in eViews, we can do CO with one lag, just print it. For instance, minus 1. That will be the lag, okay, in eViews. Okay? This is what eViews do. Okay, so let me, so this is the one which is the same as our textbook, 12.11 equation. Okay, so let me save this one as 12.11. So this equation will be, then I can identify later on I need this one, 12.11. I cannot put a point there, so I use 12 underline 11 to represent the equation. Okay? All right? Can I do the point? No. I have to put the, that's why I'm put underline. Huh? Cannot? I cannot do that? Let me see. Yes, I can. Didn't I have that? I should have that. Okay, let me see. This one is this, right? So I have equation underline 11, okay? All right, it's not dash, it's underline. Do not use the dash, underline, or to name the equation, all right? Okay, then I'll do it again with what? With distributed lag model, which is 12.12. and it shows 3 legs only. So I'm doing the same thing as the textbook shows, okay? All right? So this one is what? Okay. As an equation, and YD, so the current YD, then YD, left 1, YD, left 2, YD, left 3, YD, left 4. Okay? All right, current YD and the leg 4. Okay, so this is the equation, which you can check that with our textbook. It's a little bit different, right? The constant is difference, but the coefficient is, although it is not this, I don't have the same. What's your answer? Is the same as mine? C is constant. C is constant. But the result, it seems that is different from our textbook. What do you have? Okay. It is different, right? And do you have the same answer as mine? Huh? Up to 3? How many? Oh, okay. So let me rerun it again, okay? I thought it's 4 leg. Oh, it's only 3, right? Okay, so I'll do it again. Huh? I'll make it 3, okay? This is not right, okay? I'll re-estimate again without the 4th. It's only 3, okay? Let's do it. All right? So, well, again, 0, 3. Well, it's pretty similar. It looks okay. Yeah. Yes. Using what?
There's empty values with Excel. So if we're having errors with the computation, there's blank values.
Well, this is, this is for the previous. Okay, so,
There's no YT for the
well,
Should we just use
okay, look at this one. No, look at this one. How many observations do I have? Since I have YD minus 3, right? So originally, how many observations do I have? 33. 33, but minus the 1. I don't have it missing. So now how many observations? 29 only. Okay, they have to use what available for my original data. So whatever the data missing, they don't use that. Therefore, I have just only 29. Did you see that? Included observation, 29 after adjustments. Yeah, but I don't know how you do that. So this is by eViews, and I think the answer is pretty close to our textbook, right? If we using 3 decimal places or 2 decimal places, that'll be exactly the same as what our textbook shows. Okay, so I'm going to name it as equation 12 point, which one? 14, right? So this is 12, 14. Okay. All right. So let's see. You all get to the answers? Do you have the answers as what I have it here? Huh? Oh, okay, this is not that easy as the e-views. Okay, so maybe you can do it later on. Okay, just see our explanation. Okay, all right. According to 12, 12, then what do I have? What do I have for my beta 0? What do I have for my beta 0? Is 0 point what? 46, right? If I just use 2 decimal places, okay? Then what is the lambda? What is the lambda? 0.56. Yeah, okay. So this is 0.56, which I have it. I'm showing. Let me show the. This one, I invoke this one. Okay, so 0.46 and 0.56. One is beta 0, one is lambda, right? So do I expect all these numbers? So do I expect this is 0.46 theoretically, okay? Then all of them is the multiplication of these two. So would you like to do that for me? You multiply 0.46 with 0.56. What's the number should we have theoretically? Four, 6, 5, 6. Yeah. 2, 5, 7, 6. Then another one is using times 0.56 again, using these numbers. 14426. Okay, then 3. Now since we have 3 terms, right? So the other one is 08078. Okay, this is by theory. Then this is the result is from 1214. Okay, then theoretically we say that if we transform from 12.3 to 12.9, I think this is 12.9, right? Okay, then I should have all the coefficient smoothly decline, right? And all the signs are positive because the YD is what? Is what? Is the personal disposal income. And this is the consumption. So the disposal income with the consumption is positive relationship, right? And this one, by estimation, is positive. So I multiply this together. This by theoretically, all the coefficient decline smoothly. Okay, let's see. Do we have the same result by estimate the equation? So I'm going to put this one and turn on this one. Okay? What do we see from here? Do we have the numbers decline at? We do have the number decline, but up to the third periods become to negative, right? Although look at this one, the probability is not significant, but actually we just look at signs, which is different. Okay, and what do you thinking about why do we cause all these situations? What's the problem with this one? Look at the x variables. All the same x variables, but different lag. So this is what we say multi-collinearity. Okay? All right? This is multi-collinearity. Theoretically, I can transform from dynamic model to distributed lag model. But when I do the OLS estimation, the result shows that the coefficient can, although when we learn multi-collinearities, we know that the OLS estimate still unbiased. And unbiased doesn't mean that it's correct. It's just the distribution is bigger, since multi-collinearity caused the standard error increase, right? So standard error increase make the coefficient change it dramatically. It's very sensitive, although it is unbiased. Understand what I'm saying? So you need to identify the unbiased and the really correct. Unbiased means this number can be believed, but since the variance is increased, so with the same distribution, with the same parameters of the center, but that estimation numbers change dramatically. So if I put more lags or something else, maybe there's a different story again. But according to what we just have it, if I'm using just 3 lags, and it doesn't follow what the theoretically, expected. Okay? All right? Yes. Yes, we just want to. We'll talk about that. We'll continue to talk. I haven't finished yet. Since we learn many kinds of situations and we provide remedies, right? So we will say that also. What do you mean by original way? Yeah, what way? Do you remember what is the remedy for multi-collinearity? Do nothing. Good. It can be, it's just the sample problems. Okay? Maybe we do nothing. All right? So, this one, I like, you provide these answers. And so that's why we have some recommendation later on. Okay? Any questions? Okay, all right. So in other words, we like to say that theoretically, this distributed lag model with a dynamic model that really, is the same family member. I'm trying to say. Okay? So all the dynamic model can be expressed as a distributed lag model. However, this one has multi-collinearity problems. So I'm using OL's model, and I do have some problems. Okay? All right? And with these dynamic models, what can you see? Both of models is very useful so far. They all use this one and also this one too. These 2 models available in empirical study. Okay? Although the the problems we show. But both models is still very useful. Look at this one. Look at these models. If we have this lagged dependent variable, look at this one. And this is time series model, right? Any things you were thinking about, you learned it from chapter 9. If I have one t minus 1 with dependent variable, what you learn from chapter 9, can you thinking about anything what you learn from chapter 9? The zero correlations. If you want to check the zero correlations, Durbin-Watson statistic cannot do that. You have to do what? LM test. Remember that? We just learned it in chapter 9. Okay? So they do have its own problem, but still we still have remedies. And this one, we do have problems still, but it's still popular in the empirical study. Why? Let's explain it. Okay? All right? So far, I just want all of you to know the relationship between these two. Okay? We haven't talked about any problem with time series yet. Okay? All right? Any questions so far? Right. And there's one information. If you run 12.3, okay? And, let me see. Okay. In economics area, okay, those coefficients have some meanings on it. Okay, let's see. Let me see. Maybe I see anything from PowerPoint. Okay, where is my? All right. Oh, or I need to put this one. This. Okay. Where's my laser? Point? Where is it? Oh, here. Okay. Then next page. Okay, this is, this 12, 11. I have all the T. Look at this one. Say that. Did you see this adjusted R square? How beautiful this word. What's the range of adjusted R square? 0 to 1, right? And this is 999. So it means perfect, right? Perfect. This is the symbol of time series data. With time series data, adjusted R square cannot be believed. Cannot be believed. This one shows this kind of numbers. All the time series is just R square is just as high as possible. Because of the time series, because of the zero correlation. So the adjusted R square here, if it is for forecasting, okay, if it is for forecasting, this kind of adjusted R square is wonderful. Means the model is perfect. Okay? But if we wanted to do the relationship, okay, this adjusted R square is terrible. Means serial correlation. All right? Okay, look at the, what is this? How come this number is different from ours? Is this the same as ours? 60. Oh, the original one, we do it. Eh? But the number is different. How come the number is different with ours? 46 and 26. Oh, yeah, I'm sorry. Is the same as ours, right? So, okay, this is the result. We have it, okay? Then, okay, and how come these two numbers different? Let's put this, different legs, okay? Huh? Okay, but actually, let's see. Oh, they started talking about the zero correlations. So let me bring all the back of when we talk about the remedies. Okay. So what should I do, the distributed lag or dynamic model? Okay, and according to the past experience, if you can recognize by theoretically, if the lag is not many, I mean, if the lag is not many, like if you have just one or two, and also you are definitely know the lag, okay, and the lag is not many. If the lag is not many, means what? Multicollinear error problem is not that serious. So in that case, prefer using distributed lag model. Okay. All the researchers say that they would rather see the multicollinearity problems to fix with multicollinearity problems. They say the multicollinearity problem is not that serious if you have small legs. Okay, then it's easier to use OLS estimation. OLS estimation is still pretty popular used, and many areas prove that it still is a very good estimation method. So it's still useful in any area. Okay. And let me see anything else here. And in this models, the most problem, this is what we call the multicollinearity problems. Since this one, is still white noise, but this one cannot be white noise because with y t minus 1, and actually the current t is affected by current t, then t minus 1 will affected by t minus 1. Okay, so the zero correlation problems is the dynamic models problem. Okay, the zero correlation problems won't be distributed lag models problems, but the zero correlation is the problem of dynamic models. Agree with me? Since we do have the previous t, okay, then the previous t will affect by the previous t minus 1. Serial correlation. If I run distributed lag model, theoretically, this is just the problem of multicollinearity. Okay? Just like what we have in chapter 8. Multicollinearity problem. These models. No. Although this if I express dynamic models, it can be expressed as this way, right? But originally, if it is the dynamic model, there's multicollinearity doesn't exist here. They do have their own problem, which is more serious, which is called serial correlation problems. And the reason is since yt is affected by the previous t minus 1, therefore, in OLS models say there's no relationship with this one with the error terms. But actually, if you have dynamic models, it cannot be that way. This one is involved with this. Okay? Okay, so dynamic models, we need to fix the problem with serial correlations. Okay? Okay, so this is what we say. We'll start talking about 12.3, which is called serial correlations and the dynamic models. And since there's a serial correlations, so what do we have to do to test the serial correlations? We have learned in chapter 9, right? Right? Okay, so we can check whether we have how to check with the serial correlation problems. So if you look at our textbook, 390, the page, 390 pages, okay? Then let me go back to my dynamic model. Where's my dynamic models? Okay, EViews. Okay, which is this one, right? Where do I see my serial correlation problems? Where is it? Durbin-Watson. Look at these numbers, right? Durbin-Watson. Okay, then how do you test? How do you test that? Can we use Durbin-Watson? Since my model is this one, can I use Durbin-Watson? What's the 3 assumptions for Durbin-Watson? Just the first order. Order what? This one, right? Right? This is follow the first order serial correlation. Okay? But now I have yt minus 1, which is violate the third assumption, which say that there's no lagged dependent variables. Remember that? Then I do have lagged dependent variable. Therefore, I cannot use Durbin-Watson. What else I can do? LM test. So would you like to do the LM test using that model? So do it, okay? How do I do it? View. I can, from eViews, I can use view, then residual, then test the serial correlation of LM test, and now I have lagged 1. How many lags do I have? Just 1? Yes, I have yt minus 1, right? So lagged 1, okay? So what do you have? The result of our textbook, they're using different program called Stata. Stata is recently popular in business research. Stata. Okay, we don't have Stata program. R, yeah, that's also free, right? It's you need to use the programming, right? All the business students doesn't know how to do the programming. Okay, so Stata is the one is pulled down. All the commands pulled down. Although some of the functions they do have to have programming to support, but basically they can use that, and we don't have that program in business school. Business school only have views, and I work with accounting department. Accounting department do buy Stata program, and it can be used just only for accounting program. So we're not able to use that one. But all the result, if we can do it from eViews, that's fine. Okay? But some of the numbers may not that match is because of the programming. Okay? In other words, these examples, which shows on our textbook, is using Stata. But if I run the eViews, although the result is still the same, means what? What is this result tell you? Do we have zero correlation? Do we? Yes, right? Well, look at all this observation times R square, which is 10.32, which is chi-square distribution with 1 degrees of freedom, and the p-value is 0.0013, which means p less than, if we use even 1%, 5%, 10%, it also proves or shows the serial correlation problems. Okay? So, for sure, this is the dynamic model does have zero correlations. Okay? So look at how do we correct the zero correlations in dynamic models, okay, which is on our textbook 331 and 339. Okay, I like to show some remedies. Okay, this remedies is also including the distributed lag model, because there's two, they can switch each other. Okay, so the first methods, okay, is that if we use one of two alternatives depending on underlying theory of the model, and the remedies, it depends on the under theory is using what kind of model, as well as the sample size. Okay, so the first one is if the theory indicate only a few lags values of the x are meaningful in explaining of y, then since we have the a potential way to avoid this bias due to the zero correlation is to estimate using distributed lag model. So in other words, if theoretically the lag is only a few, then avoid to zero correlation problems, we estimate using lag distributed model instead of dynamic model. Okay? All right? This is the first suggestion. The second suggestion is by sample size. If your sample size is small, the best approach may well be continue to use OLS even in the face of zero correlations. I mean, if your sample size is small, then although we do have zero correlation problems in dynamic model, still using dynamic models if the sample size small. And why do they do that? Because they do the simulations. Okay, after they do the simulations, they know that the problem will be really cancel out if we do have small samples. The zero correlation problems can be canceled out by the problem caused by small sample size. Okay, so in that case, if the sample size is small, then still using OLS, even in the face of zero correlation in a dynamic models. Okay, so this is the topic we're talking about today. This is really basic, and this is the relationship between the distributed lag model and the dynamic models. So from next week, I'm really talking, when we say the zero correlations, we're really talking about the variable itself instead of the models. Okay, so first of all, let's identify those models. We recognize those models. Then when we talk about how to see those zero correlations, we are really talking about the variables only. Either it's y variables or x variables. Okay, then in the future, then we will talking about some AR or MA, or the combination of AR and MA, and ARIMA. We call AR is MA, and but when they integrate together, we call it ARIMA. Those are for forecasting purpose. Okay. Then in business area, we do need to talk about those assets price. Models, which is called ARCH and the GARCH. Okay, and this is all related to the time series data. So today is April 27th, right? So we have, how many weeks do we go? All the May, and including 2 weeks in June, right? So within these 6 weeks, we will talk about so many issues. Okay, so I hope I can accommodate all of them. Okay, but I should put this first. So after the ARCH and GARCH, then I will talk about the AR, MA, and ARIMA for forecasting. Okay, this is also according to the syllabus. Okay, and I'm trying to, maybe I make it those ARCH, GARCH as simple as possible, because there's a lot to talk about, and you need to know the basic foundation. So I won't talk many ARCH and GARCH, but I will talk about that. Okay, so you will understand, at least you have the basic foundation. Then I also talk about these forecasting models. So both area students can benefit from this class. Okay, for the forecasting, I don't know whether the business students doing the forecasting or not. Maybe you do that too, right? I'm not sure about it. I said, this is all your thesis, right? So I think both of the area, both students can have the benefit on it. Okay, and let me say one of the, since we still have some more minutes, let's take some times. Okay, next time I'm going to talk about the stationary and non-stationary. I think this is an important concept in time series data. When we do the regressions, we do assume all this variable is stationary. Then how do we know the variable is stationary? We have to to test for what? Stationarity. There's many methods. So we're going to talk about the Dickey-Fuller test and also augmented Dickey-Fuller test. That's very basic in time series data. And when you do the forecasting, okay, we need to know the Granger causality. Have you learned about Granger causality? A little bit, okay. This is the one in 12.4. 12.4, okay. Let me show this one, okay. So Granger causality usually is by forecasting, okay. Then I'll talk about the Granger causality. This is just what I say, okay. We just done this one, okay. Alternative one. This is I already explained Granger causality. So let's see what is the Granger causality. Granger causality is a circumstance in which one time series variable consistently and predictably change before another variable. Okay? Means that if I can prove one variable consistently happen before the other variable, then I can say this one is Granger cause y variable, the other variable. In other words, if I use a and b variable in not x and y, okay? If b is what we call y variable and a is what we call x variable, if we can show a variables without, usually it contains many legs. Okay, if we can show a variable always happen before b variables, then we say a Granger cause b. You see what I'm saying here? So this is what say Granger causality. So don't be, look at this one, don't be lured. Look at this one. I have y here, and I have this leg y, and this is a. If I can show this one always before this one, then we say a Granger cause y. But how do we do that? There's, in terms of 4 situations, you have to check. Sometimes a cause y, sometimes y cause a. This is what we say, y cause a cause y, or y. Then I'll do another another equation, or what is the model? Replace the a here, and put the a leg here, and put the y leg here. You see, this is bilateral. Okay, then there's 4 situations. And I can definitely identify which one Granger cause another one. Therefore, if you want to do the forecasting, you can use this one as the causes, then forecast another one. Okay, so this Granger causality is, most of the time is for forecasting. Okay? All right. I think we'll just stop here, and we'll continue next week. Oh, I haven't stopped. Okay, let me stop.